Hello, my name is Hojin Kim, and it is my honor to present you my work, Offline to Online Knowledge Distillation for Video Instance Segmentation. My current affiliation is with SI Analytics, and this research was conducted during my time in Professor Im Sunghoon's laboratory at Digist. Our research is focused on the task named Video Instance Segmentation. This task involves segmenting, classifying, and tracking objects in a video. Additionally, it can be applied across various fields, as illustrated in the video below, including autonomous driving and video editing. The research on video instance segmentation has primarily been divided into two main types. The first is the online method, which produces results for each frame individually. The output for a single input is stored in memory and then utilized for processing the next frame. By matching features of instances between the memory and the current frames, it ensures consistent tracking over time. The second method is the offline approach, which simultaneously produces results for multiple frames from a single input. This process does not require the matching. But inferencing whole frame caused problems like memory issue. Some researchers leveraged the clip method. This approach entails dividing the video into clips for inference and subsequently matching the results, thereby indirectly ensuring the real-time performance. The online method has the advantage of enabling real-time inference. However, since matching between memory and current instances should occur frame by frame, errors accumulate during the matching process. In challenging environment where matching is difficult, the tracking performance significantly drops. The inconsistency in the features of instances within a video is key problem of matching. Changes in size, orientation, and other factors including position can alter the features visible in the image, making inconsistent tracking. Additionally, the presence of multiple similar instances on the same scene can further hinder the distinction between individual instances. The core idea of the research originated from anchor-based feature learning. By generating anchors that can represent each instance in the entire video and training the model to learn instance features close to these anchors for each frame, it becomes easier to distinguish each instances. Moreover, anchors can be generated using an offline model. The figure describes the offline model beta, capable of generating instance features using the entire frame. Utilizing an offline model allows the creation of instance features based on richer features from the entire frame. This approach ensures that the features remain representative even at the frame level. In summary, we generated instance features using an offline model and transferred this knowledge to an online model in a teacher-student fashion, completing the idea in the form of knowledge distillation. We term this approach Offline to Online Knowledge Distillation, or OOKD. The overall structure is as follows. Initially, the student model learns features for each instance from the teacher model while simultaneously undergoing its own training. The teacher model generates instance features using the entire frame. The generated instance features are then utilized by the QFA module, which constitute a core contribution, and it will be elaborated later. Both online and offline model is composed by transformer-based architecture, and each core in transformer represents the corresponding instances. The student model is based on either architecture and serves as the target for training. Since our focus is on model training, there were no modifications made to the inference process. On the other hand, the teacher model is based on the Vita architecture and participates in training while being frozen. The QFA query filtering and association model was devised to serve how to align the features. We recognize that features not accurately representing instances in both the teacher and student features could negatively impact the training. Therefore, we designed a module to filter out features that do not correctly represent the instances. In this module, each instance is matched with ground truth, receiving the corresponding ground truth ID. Through this process, inaccurate features are not matched and thus do not participate in the training. We scored each feature based on how accurately it represented each instance, and we formulate the scoring mechanism as an equation. Bounding boxes and class heads were appended to the features to generate the bbox and class score for each instance. We then get the scores using cross-entropy loss and IOU loss. The matching pairs were computed using the Hungarian matching. Using the matching pairs generated through the aforementioned method, we applied cosine similarity loss to train the models, training the features to become closer. In this process, matching pairs were created for every instance appearing in the frames used as input to the online model. Finally, the knowledge distillation loss generated through this process is added to the original idle loss. As a sub-contribution, we address a class imbalance issue in the YouTube VIS 2021 dataset where the human class was predominant and minor class like scores had lower proportion. We proposed a technique called minor paste. This is an extension of the copy-paste method, where the probability of sampling a minor class object during the copy process is increased, ensuring more frequent sampling of minor classes. The following are the experimental results. We conducted experiments on the YouTube VIS 2021, 2022, and OVIS datasets. An interesting observation is that the model idle, despite being an online model, was the state of the art at the time and outperformed other offline models. However, the OOKD model, which learned from the offline features, exhibited superior performance compared to the original idle model. This indicates that even if the performance of an offline model is lower, the offline features can be still effectively utilized. The following is a qualitative comparison of results. In the original model, the first giraffe disappears and reappears, causing a changes in the distance ID. However, in the OOKD model, this issue has been solved. The improvement is even shown in scenarios with a high number of instances and overlapping situations. OVIS dataset is the most challenging dataset than other VIS dataset, but the same improvement was still sustained. The following is an evaluation study comparing MAP in long and short videos in YouTube VIS 2022. Table 1 demonstrates the impact of the QFA module. Without the QFA module, applying knowledge distillation results in a slight performance drop. However, when the QFA module is added, performance improves with a more pronounced effect observed especially in long videos. This provides evidence that the model was trained with the intention of improving tracking performance. Table 3 represents the effectiveness of the minor paste. When using simple clip paste in videos, there is a slight performance drop. In contrast, when applying minor paste, the performance is increased. It is end of presentation. If you have any question, please let me know and feel free to send me an email. And thank you for your attention.